Good afternoon, everyone. My name is Ismael. I'm the founder of Lagrange Labs. So today we're going to talk about a new interoperability primitive, zero-knowledge data parallel computation. So before you roll your eyes and expect another talk about how ZK interop works, let me stop for a moment and say the space of interoperability is far larger than we give it credit for. In particular, we typically think about zero knowledge in the context of how do we make interoperability more secure. In reality, there are a lot more uses of zero knowledge and interoperability besides that simple question. In particular, there is the question of how do we make interoperability more expressive? How do we take an assertion of state that is moved between chains and do more with it? So, let's start with a hopefully not controversial statement. State machines require state. Yet, when we think about increasing the expressivity of what we can do with a state machine, we typically think of enhancing the execution environments, about having new types of front-end languages supported, new types of state transitions supported, and we don't often think that state transitions and state machines are fundamentally constrained by the state that they have access to at the point of a transaction. So let's take a step back. What is state? You can think of the state of a blockchain as the store of all contract values, all variables, everything encoded at a point in time in a given block header. Given that these are blockchains, the state of one block is inextricably linked to the state of the previous block. So from a given block, you can really figure out cryptographically what any contract value was at any point in time on any blockchain from a single block header of that chain. Now, how does this work with cross-application state access? In the monolithic context, we typically have a single execution environment, right? The virtual machine of that chain. If you're on Ethereum, that's the Ethereum execution environment. If you're on a rollup, that's the rollups execution environment. And if you're on a Cosmos chain, that is whatever the execution environment of that Cosmos chain is. All storage is in the same tree. If you're in Ethereum, that's the MPT tree. If you're in Cosmos, it's the IVL tree. But everything is in the same data structure and the same block header. Access is therefore simple. You're basically having all your data co-located in the same place. Now, what about the cross-chain context? Where is data? Intuitively, if you have a separate execution environment and a separate block header and a separate block time, data is not co-located. It is fragmented across a series of different locations, a series of different execution environments, and the only way to access that is with cross-chain protocols. Fundamentally asynchronous, messaging and bridging. Now, what about IBC? IBC is a tremendously effective standard for trust-minimized messaging and state queries. In its current form, it supports messaging and querying of different contract states across compatible chains. But what about historical data? What about compute or building applications that span longitudinally? For example, if I am on Osmosis, or sorry, if I'm deploying a new chain and I want to compute the volatility of an asset pair in Osmosis, it's an options protocol, and so I want to do Black-Scholes, so I need volatility. Well, how do I do that? How would I use IBC to be able to compute the volatility of an asset pair for the last 5,000 blocks, 10,000 blocks? The really only way to do that would be to send messages back and forth from every single block between two chains, or query every single block between two chains to try to figure out and derive the correct data. So in reality, this is not a very effective paradigm because you would require a near total synchronization of two chains to access that longitudinal data. And what's more likely, and this is what developers do today, is they rely on an off-chain oracle. So you have a chain-to-chain problem with interoperability, where functionally you can solve that with better tooling on top of the existing infrastructure. The issue is not security. The issue is expressivity. How, with this secure connection I have between my app chain and Osmosis, how can I derive the relevant data without requiring an off-chain dependency? And this is the environment that we exist in today when developing applications. You have what is fundamentally a data lake of on-chain state. State is fragmented across thousands of potentially modular rollups, application-specific chains, and differential execution environments. Blocks, version data structures can be thought of as a table in that database or a single snapshot of that database. And the majority of that data is not available to applications at the point of execution. You can't query it, you can't search it, you can't compute across it. You're constrained by what you can do. And so to summarize, if I want to know very specific properties of a chain at a certain point in time, I can do that. That's what these state machines are great at. So who owns NFT X in contract Y? Easy. What is the price of Juno to USDT on osmosis at block N? Easy. But when I want to now do things that are more expressive, what is the price of Juno to UST over the last N blocks when factoring out outliers? What is the volatility of Juno to UST on osmosis, summed up with the volatility of Juno to UST on JunoSwap over the past N blocks? This is where existing technology is unable to address these questions. And so this is where we get to what our team at Lagrange Labs builds. So what we build is a proprietary proof construction called ZK MapReduce, which allows us to compute large-scale batch proofs of contract state concurrently with dynamic data parallel computation. So that's a mouthful, but what this allows you to do is to derive the on-chain properties that are intrinsic to your application trustlessly without incurring additional off-chain dependencies by doing all of this in zero knowledge and then verifying that on-chain with respect to a secure block header source. And what is a secure block header source? Well, a secure block header source can be derived from IBC, it can be derived from a messaging protocol, it can be derived from a bridging protocol, it can be derived from wherever you trust in terms of your application. And now you can have this type of dynamic and expressive computation that inherits directly from that predefined point of trust. So in practice, this lets you treat on-chain data like a data lake, like it's in your Web 2 database. You can compute across it, you can query it, you can run SQL on it, and you can verify the result of that back on-chain using IBC, using any existing cross-chain framework that you trust. So these proofs, as I mentioned, are transport layer agnostic. So if you want to use IBC or a third-party protocol, maybe an Axelar, a Hyperlane, a Polyhedra, Layer 0, we're unopinionated on that. If you trust it with your application as a developer, that's great. These proofs can be verified with respect to that predefined point of security, which means you can take that block header, you can take that assertion of state, and you can now do more with it. You can, for example, determine the users of a DAO who have voted over a predefined period of time verifiably so you can issue rewards to them. Or you can have a derivatives protocol, and you can compute across that protocol with so you can compute across the options. So you can have an options protocol, and you can compute across the DEX that you want to use to derive volatility verifiably. And you don't have to now incur an additional application-level dependency on an off-chain data feed. You can basically use the existing application logic you have today, the things that are inbuilt with the Cosmos SDK or with IBC, and you can now do more with that underlying connection and underlying data. So how is this possible, and why is this possible? And this comes down to an innovation in applied cryptography that our team has been able to unlock. And what this is updatable zero-knowledge proofs. We've typically discussed zero-knowledge proofs in the context of these difficult-to-compute, highly resource-intensive proofs of the execution of some code over some predefined data set. But in reality, once you generate a proof, there are components of it that you can reuse between subsequent executions of that underlying computation. And so that means you can take computation that was used to derive a proof on an overlapping or non-overlapping data set and compose that back together to create something new. And what this means is on the marginal run, we can substantially reduce the time it takes to generate a new proof. So if you want to do volatility over block n to n plus k, and then now you want to do it from n plus 1 to n plus k plus 1, you can do so without incurring an entire rerun of the overall proof generation. So you can have very, very fast updates of your proofs and computation of your proofs without requiring incredible amounts of duplicate computation. And so what this does is it lets you minimize proving time and scale your computation through proof composition rather than through using incredible amounts of computation of the arbitrary run. And so this allows you to have these low overhead, highly expressive data connections between chains that make your application far better in terms of its access to data. And so for more information on how this works and on our team's breakthrough with this primitive, we'll be giving a talk at SPC later this year in August that outlines the full details of this construction. So expect also a testnet launch around this point as well for certain early supported use cases that we think are going to have rather large and far-reaching effects, both in the modular context, the Cosmos context, as well as the EVM first context. So thank you, everybody.